Hello my little friends, and I hope you're all well and everything's sort of going well. I need to get the sort of coursework or the definitive sort of version of the coursework okayed for this when I think about it. So we'll discuss that tomorrow in our Teams meeting, what you're actually sort of wanting it to be. I would imagine, as usual, you'll never be able to bloody please everyone. I mean, what will sort of happen is people will be wanting an easy option, and there'll be the odd person in the class that wants to challenge themselves, so we need to get a sort of balance with that. Regardless of anything, I mean, we'll have a sort of class test, which will be worth about 40%. Then the labs are supposed to be worth 30%. Then there's supposed to be a practical coursework as well, which is 30%. But we can sort of intermingle the labs and the practical coursework in order to adhere to people's ability. Because as you know, in this module, we've got direct entry students, we've got continuing students as well. So it is a bit of a thing. I'm actually in consultation with the higher education of the UWS Academy in order to make that transition from college a little bit more smooth. So we're working on that. However, today we're looking at polymorphism. This could very well be entirely revision for everyone, or maybe even the same sort of slideshow from programming with objects. If I did it in programming with objects, I'm not entirely sure. It could have been one of those sort of option things where we decided to sort of look at it. But anyway, if you've seen these slides before, I apologise. And if not, then it's new stuff for you. Mind you, it is sort of revision, so I mean, I have had people in the course before sort of say, well, we've seen this before, we know it. Well, actually, no, you don't know it. You're not really that proficient at it. So it would be good to go over it again. It is a sort of key principle of object orientation, and you need to sort of understand it anyway. So it's good to go through these things once again. So I mean, if you have seen it before, then hopefully this will stimulate the brain cells. So polymorphism, and I'm wearing my IT t-shirt with purpose, I might add. So polymorphism is only possible through inheritance. So you have to be able to understand inheritance first. So obviously polymorphism is a little bit of a more difficult, complex concept in that regard. So you have to understand that first. So that's why we did encapsulation, inheritance, and then this. And the first one, the first lab was methods, functions, and a sort of timer. So the word polymorphism. So poly means many, and morphism means forms. And that is why I'm wearing my IT t-shirt today. I'll maybe wear it tomorrow. It depends on how much I sweat today, basically. I doubt I will very much, but I don't like wearing the same t-shirt 2 days in a row. But anyway, many forms. Okay, so the entity of it, if you're a fan of Stephen King's It, takes many forms. And one of those forms is a big spider. Its favourite form seems to be a clown. It's Beverly's dad. It's Mike's burnt parents or burning parents or whatever. It's a leper. It's a werewolf in the mini-series. It's many forms. And I think that's one of the sort of weaknesses. It's beautifully illustrated as well, because it's one of the sort of weaknesses of the entity and how they sort of slightly beat it in the book a little bit. And also in the film at the end, the first chapter of it, the children all see it in its different forms when it's sort of shape-shifting, and they batter it to death, because it's actually, its main sort of weakness is that it's limited to the form that it's in. That's the sort of limit of its power, and that's actually quite apt when you're talking about polymorphic objects, because they behave dependent on their object type. Okay, so essentially, whatever form it's in, that's the weakness, and then the objects behave in a particular way dependent on the type of the object. Okay, so do try and sort of remember that. So the idea is at runtime that the variables are actually changing behavior, okay, because they're actually changing data types. Brilliant, okay? So just like it is changing behavior because he's a werewolf. Cool. A parent class variable referring to an instance of a child class. Okay, One of the main pillars of object-oriented programming, polymorphism. So we've been through this sort of thing before, encapsulation, abstraction, inheritance, and polymorphism. Those are the four main sort of pillars of object-oriented programming. There are other things as well that we could cover, but anyway. A member function that will produce different results depending on the type of object for which it is being called. So if you imagine a sort of, and we'll go through a number of groups, I've got a cooking lab for you today, so sort of make that available for you to try. I'll also try and do the lab sort of live tomorrow for you guys as well, so that you can sort of copy the code along with me, hopefully. It will work that way. So imagine a group of enemies, and through polymorphism, you can call the attack member function, and the result will be different for what type of enemy it is, and they will be related through inheritance. So I've got a number of examples in the lab, and a number of examples in the lecture slides for you, and one of them is shape. Now, when you're talking about actually drawing or moving and then redrawing a shape, if I were to say to you, draw a shape, you wouldn't necessarily know what to draw. So you would have a sort of shape class that would have the sort of basic behavior, of course, and then you would have other classes that would override the drawing function in the base class. You don't really need a drawing function in the base class. It would be a pure virtual function, I think. And you would never have, it's an abstract class, you would never really have an object of type shape. You would have an object of type triangle, an object of type circle, an object of type square or rectangle, and these of course would be drawn. These would be shapes, but they would be drawn in a different way depending on the type. So that's one way to think about it. Another way, another example that I've got is an enemy, and then a particular instance of it, a boss. So they of course have a sort of overriding taunt or attack or something like that. So think of it that way. Another example that I've got is a sort of monster abstract class. At the end, this is the complex example of polymorphism that I've got in the labs. Essentially you have a monster class, and then you have werewolves, vampires, zombies, mummies. Yes? And the way that they attack and the way that they behave is different. But if I were to say to you, how does the monster attack? You don't necessarily know because you don't know the classification of the monster. What does the monster actually say when it attacks or something like that? Or what sort of behaviour does it exhibit? You don't actually know what that is. And it's only by classifying the type of the object or the variable that then dictates what that's going to be. So if it's a vampire, they're going to attack by trying to suck your blood or something like that. If it's a zombie, they're going to try and eat your brain. That sort of thing. So I've got those sort of three examples in order to sort of hammer it home to you. And I think, I'm not going to lie here, they are utterly 100% brilliant. They are the brainchild of me. Yes, they just come out of my brain when I'm in the cross trainer or whatever, or in the bike. Yes, so that's what I sort of do. Plan little lessons for you guys when I'm on these things. Exercising. Good stuff. So, consider the following example relevant to computer games. You have the game object, the update, the draw, player, which inherits from game object, enemy, which inherits from game object. Then you get two kinds of enemy. Okay, so think of that. So you've got a normal zombie and a teleporting zombie. Not that I've ever seen a teleporting zombie in the history of ever. I saw this sort of example on YouTube, and it seemed to be a teleporting zombie example. So I decided, okay, that seems all right. But anyway, what you have here is a normal zombie. So that's the object being declared in a sort of static fashion. So a normal zombie, zombie 1 is equal to a new zombie. I'm sorry that this isn't in colour actually. Is equal to new, we call it normal zombie. It should be normal zombie, not simple zombie. So zombie1.update, rotate and turns to the player. You've got a teleporting zombie, which was zombie2 equals a new teleporting zombie, so that should actually be normal zombie, okay? And then if you say zombie2.update, then that rotates and teleports to the player, okay? So what you're actually doing there is you're overriding the update in the base class. So you'll notice that zombie1 and zombie2 both have an update function. And depending on what particular kind of zombie they are, whether it's a normal zombie or a teleporting zombie, the update is different and is overridden in the base class. Okay, fantastic. Oh, right, I said that. Overridden the method inherited from enemy. Okay, that's exactly what sort of happens there. Good stuff. So the question is, can we now have this? And just to understand what is happening, we have to look at the sort of assignment operator here. The data type on the left-hand side has to match the data type on the right-hand side. So an enemy is a zombie equals a new normal zombie. Now, can you actually have that? Let's ask that as a question. So on the right-hand side, it looks like a normal zombie, but still an enemy because of inheritance. Okay? Can you have that? So you may be asking this. A normal zombie, can a normal zombie be a new enemy, right? So it depends on the assignment. They've got to be equal, okay? So you can have that, that's perfectly legal. Can we have the opposite? Can we put an enemy into a normal zombie? And of course the answer is no. This is because even though a normal zombie is an enemy might not necessarily be a normal zombie. It might be a teleporting zombie. Okay? So even though a normal zombie is an enemy is not necessarily a normal zombie. Okay? So do think about that as well, and it depends on the sort of assignment. So I hope I explained that reasonably well enough. Okay? So you've got to look at the sort of inheritance hierarchy there and make sure that you sort of understand that the assignments have to be the same on the side. So there you go. When we kind of look back in that, normal zombie is a zombie equals new enemy. Perfectly legal. Okay? That's fine. Oh no, sorry, I beg your pardon. That's not legal. This is legal. Enemy zombie is new, normal zombie. That's perfectly legal. That's still an enemy because of inheritance. On the right hand side it looks like a normal zombie. That's absolutely fine. But this is illegal, so apologies for that. Normal zombie is a new enemy. You can't have that. Okay? So just to sort of recap there, even though I confused the issue. So even though a normal zombie is an enemy is not necessarily a normal zombie. Okay. So if we look at the code, we've got an enemy zombie equals new normal zombie, zombie.update. Okay. The enemy will update like a normal zombie, and the reason for this, that at runtime, that particular zombie is a normal zombie. Okay. If later we then say an enemy zombie is a new normal zombie, zombie.update, fine, fair enough, then zombie is then assigned to a new teleporting zombie. The update will then be different. So the case is a bit wrong in some of these cases, but never mind, the example still sort of stands. So then it'll update like a teleporting zombie. And again, the reason is because at this point, at runtime, now that's the key thing to remember, at runtime, it's a teleporting zombie at that particular point in the program. So at this point in runtime, it's a normal zombie, yep. And then when we get to here, yep, it should be a lowercase z, it is then a teleporting zombie, which then, of course, affects its behavior because its type has changed and the behavior is dependent on the type, how the method is overridden in the base class. So what's happening? The idea is at runtime that the variables are actually changing behavior because they're actually changing data types. Okay, so a parent class variable referring to an instance of a child class. So why does it work? Relies on inheritance. Looking at this particular class hierarchy, a game object has an update and a draw. Since an enemy is a child of a game object, it can either inherit those methods or it can override them. And the same is true for normal zombie and teleporting zombie. So we look at our code, we know that the code to these methods is guaranteed to sort of be there. Okay, now here is the true power of polymorphism. Prior to all of this, you would have a list of normal zombies and a list of teleporting zombies, right? Okay. So I've taken them from Plants vs Zombies. This is a sort of normal business one, obviously in the business suit. That we've never. This used to be me going into the university, not I'm drawing parallels of being a lecturer and being a zombie. It's not quite the same thing. But anyway, this is me going to the university. And then after lockdown, I just decided I'm just going to run everywhere. And I lost a wee bit of weight, which is great. But anyway, you would have a list, okay? A normal zombie list and a teleporting zombie list. So here is the true power. So two separate lists. And this is not really what we would like to do. It would be nice if we could combine all of this into one particular list. Yeah, so that's sort of wrong. So this is exactly what we're going to do. So in this case, you can see that we have a list of enemies called enemy list. And as we begin to iterate through this list, notice that we change the syntax just a little, okay? That we now say for each enemy E in the enemy list, when E points to a normal zombie, it will in fact, or when it points to a normal zombie, it'll update. Okay? And when it points to a teleporting zombie, it'll update. So you just got an enemy list, okay? That goes through every single one of them. And then you can have all of these, right? So dependent on the behavior, you can then update it, okay? Or depending on the variable, it will update its behavior, okay? Fabulous. So, the parent variable is referring to an instance of a child. The variable changes behavior during the runtime, as I haven't said that enough, because it's changing data type during runtime. So a very common question for employers, and I got this from, I believe, a programmer at Morgan Stanley, who's a graduate of the computer games technology course. And what is the difference between inheritance and polymorphism? So it'd be nice to have some form of answer to that, a sort of scripted answer that looks natural before you actually go into an interview. Now, don't think that just because you've sort of breezed over something that you actually know the answer to that. So, inheritance, I would say, write down a definition of inheritance, write down a definition of polymorphism, and then say exactly why the two are different. Now, I don't know if any of you are a fan of True Blood, but there's this sort of monologue that Russell Edgington does. I believe it's the end of season 3 or something like that. And it's when he sort of goes on to the news, he kills an anchor man, and then he goes into this great big tirade about how we are the face of vampires. And it's absolutely 100% brilliant. We will eat you after we eat your children. Not time for the weather. Tiffany, you know, it's brilliant. Anyway, have a look at it. But the main point of that is that guy, Dennis O'Hare, I believe is his name, rehearsed that for approximately 3 weeks to make it look as if it was entirely natural. Now, you can imagine actually going round about your mansion, your flat, whatever, rehearsing something for 3 weeks to make sure that it's actually in there. So do rehearse these things in your brain, and I'm not just talking about being able to write the answer to a question. I'm actually talking about saying it as well. So, I mean, visualize being asked these particular questions, yeah? And then visualize being in an interview and then actually saying what your response is. And it's amazing when you say, when you actually do something like that, do a sort of practical exercise like that, even though you think you can organize and BS an answer in the spur of the moment, it generally doesn't work that way. It will be very, very surprising how it actually sort of comes out. So get into the habit of being able to accept your sort of limitations, your flaws as a human, and being able to verbalize your answers in a sort of rehearsed but natural looking form, and do sort of try it. I'll give you a sort of example of that. I was trying to do a sort of video for the entire program, and it was 5 minutes long. To be 5 minutes long, I had to put everything but the kitchen sink in there, say why the program was great, what it actually contained, all that sort of thing, what kind of teachers are on it, what are the lecturers like, absolutely everything, the content, what kind of jobs the students get, everything. accreditation, how many lecturers had won awards, that sort of thing. So I had it all pasted round about my laptop to make it look as if it was completely and utterly naturalistic and intrinsic. And do you know that it took me from about 10:30 in the morning to 3:30 in the afternoon before I even got a version that I was happy with. So when you're thinking about going into interviews and things like that, make sure that you can actually say what the answer is going to be, instead of thinking, oh, I could say that, and then stuttering over an answer like a twit. So make sure that you rehearse these things. Just my piece of advice for the day. So what's the difference between inheritance and polymorphism? Inheritance is where you absorb the properties of another class in a derived class, and polymorphism is where you override the properties of a parent class in a derived class. And then, of course, you can actually add to the fact that polymorphism is only possible through inheritance. So do remember that sort of thing. I used to teach 2D graphics programming in computer games technology. That was way before any of your time. And it's quite fun, I quite enjoyed it actually. And the example given to illustrate polymorphism in that particular example was drawing these things in OpenGL, and it was a show member function that was sort of overridden. So all the shapes inherit from a base functionality from shapes, so the circle, rectangle, triangle, as I sort of said, and the show produces a different graphical output for every single one. Now, I think I still have that program somewhere, but anyway, we're going to do a sort of, in the lab, a little bit more of a sort of minimalistic, just textual version of that. But anyway, there you have it. You've got shape, circle, square, and triangle inherits from all of that. That's absolutely fine. So you've got your shape class, and you've got a sort of public virtual void draw. Virtual void means it can be overwritten. And then, okay, you've got in here you've got console.writeLine performing base class drawing task. Now that line of code should never really be reached because you have it will be overridden in the inheriting class. Okay. So in this class, you have to have a virtual void function that will be overridden by functionality in the derived class. So essentially, this is a bit pointless. It's just there to fill a bit of space, to be honest. Then you have class circle, which inherits from shape. You've got your constructor there saying that a new circle has been created. And then you're saying public override void draw. So that's overriding that, okay? We'll do all of this in the lab, sort of together, even though we really shouldn't. It's part of an assessment, but we'll bloody well do it anyway. And you're overriding the draw in the base class, so it's performing the drawing of a circle task, okay? So remember that circle has to inherit from shape. You need a constructor. Notice there isn't one in the base class, so you don't actually need a bunch of shapes coming into existence, I suppose. Is that right? Yep. Fantastic. And then this is the override function, which replaces the functionality in the base class. Okay, so then you've got square. Notice that these are cunningly interlaced within the slides, intermingled in there, so all the answers are sort of there. It's not as if I expect you to draw this out of the recesses of your brain. So class square inherits from shape. Once again, you've got your constructor. You've then got your override draw, which overrides the base class functionality, or the virtual void function. Remember, has to inherit from shape, so it's the exact same thing. Very, very easy when you think about it. You need a constructor, because there isn't one in the base class. That's an abstract class. And this is the overridden function, which replaces the functionality in the base. Now, to hammer home the point, we have a triangle now. And let's see, you have that inheriting from shape. You have a constructor. There isn't one in the base class. And there is an override function which replaces functionality in the base class. So easy peasy, lemon squeezy. And that's just to show you the sort of formulaic nature of it all. So there you go. Next, we have the idea is at runtime that the variables are in fact changing behavior because they are actually changing data types. So what we're going to do is we're going to have a list of shapes called all shapes. And that's going to be a list of type shape, which is great. Okay. Then what you can do is all shapes.add new circle. A new circle will be created. You can do this as many times as you want. All shapes.add new square, new triangle, new circle, new square, new triangle. Yep, file them all in. And then for each shape in all shapes, we're just calling the draw. And dependent on the type, it will draw a different thing. We'll actually allow it to put something different to the screen. Okay, so that's a sort of reasonable demonstration of polymorphism. And of course, if you were wanting to sort of, well, I think we sort of can randomize that with a simple sort of for loop. Just assign these particular things a random number from 1 to 3, and then create a shape depending on what that number is. So the list is a dynamic data structure object holding the variables in a specific order, and the type of variable that the list can store is defined using the generic syntax and tastic. And we can also store lists of user-defined objects, which in this case are shape. At runtime, the variables are actually changing behavior because they're actually changing data types. I love it. Fabulous. Okay, this is a sort of example. This is C++, and I apologize for this. We're going to do it in C# in the lab. But anyway, you've got a class enemy. You've got a virtual enemy. A void taunt, virtual void taunt here, which doesn't really actually have anything in it, although it is sort of there, it'll be overridden, I suppose. So there we have that. You're basically sort of overriding the virtual taunt and making sure that the boss has that. So, okay, inheriting from enemy, we've sort of seen this before. This is just supposed to give you a little bit of a C++ experience if you want it. You've got the taunt, and he says both things really, so you've got a virtual sort of override of that. So there we have an object of a derived class is also a member of a base class. So the boss is an enemy. It's important to use a pointer when it's C++ because you don't require to know the type, and it allows you to deal with objects. So also this means when vtaunt in boss is overwritten, and the correct version of vtaunt is called based on the type of the object and not fixed by the type of the pointer. Now that's kind of horrible to be perfectly honest. But anyway, we're going to do that example in C#. So to enable the polymorphic behavior, you have to declare a virtual function. It's virtual in enemy, and it's inherited as a virtual function in boss, and this means when vtaunt in boss is overridden, and the correct version of vtaunt is called based on the type of the object. Okay, excellent. So this is a 2D graphics example. That was in C++ as well, and you notice that in order to get the polymorphic behavior, you have a list of pointers of type shape. Okay. And it's an array of 100, and then we're sort of randomizing what that's actually going to be, setting a color as well, and that's fine. And then you sort of go through every item in the list, every item in the array, every shape, and then you're going to move that particular direction, and you're going to draw it again. So that was just a wee bit of C++. Forget those two examples, wasn't really particularly helpful, but I just sort of left it in there for the purposes of illustration. Abstract classes, sometimes it's necessary to define a class that acts as a base class for other classes, but there's no point in instantiating objects from that class as it's quite generic. And the shape class is an abstract class. In a game's context, think about enemies, so we'll get pixies, dragons, orcs, urukai. These are all really creatures with a health value as a data member and a greeting for a member function. However, it makes absolutely no sense to instantiate an object creature because you don't really know what that is. So once again, this is a sort of C++ example. So there's a pure virtual function, one that doesn't really require a definition, okay, in the class for the member function. In this case, it doesn't make sense to have a greeting for a creature because you don't actually know what it is until you know what the individual creature is. so it's obviously always overridden. Okay, fantastic. So once again, that is the exact same sort of thing. Now that's in C++, and we're going to do an example in C# to sort of show that off, the taunt thing, I think, or for the enemy. But this is the main mummy daddy polymorphism example that I've sort of got, and I learnt. And I came up with this example on the treadmill or on the cross trainer or something. And I thought, let's have a monsters example where we actually have a monsters abstract class, which is absolutely brilliant. And then we have different sort of monsters. We'll get vampire, mummy, werewolf, and zombie. Yes? So we've got, how do you call, Luke Evans from Dracula Untold. We've got Imhotep from The Mummy. And then we've got Frankenstein here, and then we've got the Wolfman, who I absolutely love. And each one has a name, age, food type, an attack, and move. So these are going to be the common variables. Now we define what these are. So common variables, it doesn't really particularly make sense to have them as common variables, but they would have common variables in some capacity perhaps. And these are the unique variables, okay? So we'll get food and type, at least that's what we're defining in these examples. Then we'll get unique functions, but are very similar, okay? So here we have an abstract class, which is a monster. We're going to have a name, age, type, food. We're going to set the properties. We've actually got a constructor for monster as well. And that just sets the name and the age, okay? So when we actually create any form of monster, that's going to be absolutely fine. And it's going to inherit these pieces of functionality from, you're not actually going to have an object of type monster, but you're going to have an object of these particular types that inherit from monster, okay? So you've got the public monster constructor. You've then got a public virtual void attack, so basic attack is executed. This is pointless having this in here, it's just overridden, yeah? The attack is overridden, the move is overridden, and then you can print the monster details as well, which is good. So, now you'll notice that this is all sort of here, and it's absolutely fine to more or less copy and paste all of that in, but we will sort of go through it. So you've got a class vampire of type monster, which inherits from monster. You've then got your constructor for vampire, which then passes in the name and the age, which are common, and you're getting the name and the age from the base class, or it's sort of from the initiating in the base class, right? So the type is then vampire, the food is blood. You have a sort of basic override void attack, so you get base dot attack. Oh, sorry, it's not overridden, I beg your pardon. Let's just have a look and see what I'm saying. You've got a sort of basic attack that can be executed, so you can actually call that if you want. You're not necessarily restricted to it, but you can do it by saying base dot attack. Oh, that's good, that's good. That's good to see that. Or you can override it. So those little bits of code actually weren't for decoration. It wasn't a pure virtual function. Okay. So you get base dot attack, which you can do, and then you can actually say blood-sucking biting attack executed, which is specific to vampire. Okay, then you get the base dot move. Once again, that's you calling the monster type move in the base class. Notice that you've got the base class here for the name and age. Okay, and then you've actually got it saying turn into a bat. Okay. Again, for zombie, which then inherits from monster, you get zombie, brains, you get the base attack, biting skull, brain sucking attack executed, and then becomes enraged and runs like in 28 days later. But you've got the base dot move as well. You get the mummy, the food is organs perhaps. Then you get the base dot attack, which is called, and then the sand summoning attack is executed. Fabulous. And then the move, base dot move, turns into a swirling sand tornado. And the exact same for werewolf. So it's just to sort of show you that this is quite formulaic in terms of polymorphism, but it's all good. So you've got werewolf constructor, the name and the age. The type is going to be specialised in terms of werewolf and human hearts. It's going to be the food. And then you've got an attack, which is a base dot attack, and then the console dot write line is mauling, howling attack executed. And then an override void move, so you've got the base dot move, so you're not necessarily restricted to what's going to be in this new thing, but you can access the base functionality too, and it turns into a wolf and lunges. So, got all the code to sort of write for this too. So in the main procedure, we're creating a list of monsters, we're creating a random object to generate a random number, okay, in order to assign what those monsters are actually going to be. You write a for loop to create 1,000 monsters if number is equal to 1, and create a vampire called Dracula who's 3,000, insert him into the list. If it's 2, you're creating a zombie called Frankenstein who's 500, and insert him into the list. If it's 3, a mummy called Imhotep who's 4,000, and insert him into the list. And then poor Lawrence Talbot, who's only 30, we're just going to put him into the list, and he's number 4. So great. Then we'll cycle through all the monsters and call the following functions. We're going to print the monster details, we're going to move, and we're going to attack. And it's absolutely brilliant in that regard. So you get a list of monsters, okay, all monsters, and these are of type monsters, but they actually are vampires. They are in fact specialized as well. So you've got a random number generating within a for loop. It's going to be 1 to 5. And then if it's going to be 1, then you're creating a Dracula. You can add that to the list. If it's 2, it's going to be a Frankenstein. You can add that to the list. If it's 3, mummy, add it to the list. 4, werewolf, and add it to the list. Okay. So there's all the sort of code there. And then all you really need to do is say for each monster, i.e. in all monsters, you're going to print the monster details, you're going to move, and then you're going to attack. And then we can see exactly what the output is going to be. Now that will give you a great big, huge, massive output that will last it'll probably take about, let's face it, 20 seconds to materialize on the screen. But once it actually has done so, you can then go up and down and scroll up and down. You can see that there's randomization that's taking place. And although you're just printing out a list of monsters, they are all different based on their particular type, and therefore have different behaviors. Okay. You can also split this code into sort of multiple files, but I don't really want to particularly get into that. This was a sort of C++ example, but you can do it in C# as well. For the purposes of this example, we'll have everything in the same file, but you could put these all into different classes all on their own. It doesn't make much of a difference. And that's how you sort of do it in C#. C++, but in C# you just create different classes, and they can all see each other because C++ is a bit evil. So there's no need for includes in relation to the classes you create, and we only need to only with using libraries such as system.diagnostic. Okay, so that's it really. We'll do this together. Sorry, I get sort of slightly mixed up in the middle, I think, but I'm not doing it again. But we'll do this tomorrow. I'll try and talk through the slides again, and we'll then sort of try and share my screen, and we'll try and implement everything together. And that means that everyone will manage to hopefully get that part of the lab. So that's lab 4 sort of done. And we can also discuss the assessment as well. Okay, right, fantastic. So, good, my little pals, and I'll see you later. Bye.